Triangles have been a very important part of our civilization for centuries now. Bridges use triangles for their incredible strength. Houses use obtuse triangles to keep snow off of them. The ocean uses triangles to make sure that
you never return.
Triangles have been a part of the greatest mysteries, the most powerful beings, and the magnum opus of food design. Now, another one of the great things about triangles is that you can figure out all the information of a triangle with only a few known facts about it. For example, if this demonic triangle has all of its side lengths as 1 foot, then we know that this dapper triangle is isosceles, equilateral, and has 60 degrees that come in threes. Alright, but how do we find out all this information? With math. But more specifically, we use the law of sines, which shows how the side lengths of a triangle relate to its angles. This is great because it means we can figure out all the information we need to about a sentient Dorito. But also, it's very inconvenient, since my calculator doesn't have a sine button on it. With that, I am left with only one option left to figure out the angles and side lengths of pizza. I will construct a program in Unity to take inputs from me and use them to construct and label a triangle. Or I could just use the scientific calculator built into pretty much all computers. It is currently Thursday, and I'm giving myself until next Friday, or 8 days, to complete this program. The program should be able to take inputs by the user, use the law of sines to determine the sides and angles of the triangle, figure out if the triangle is possible, and then, and only then, construct the triangle. With that said, let's draw a triangle. Alright, so before we draw a triangle, we are going to need to draw some points. In math, points are zero-dimensional objects that represent a position. They have no length, no width, and no height. Now in this simulation, I will give the points a little length and height. If I didn't, you wouldn't be able to see the point, and there's no point in that. Anyways, I created a prefab of a point. For the purposes of this video, a prefab is any object that I can create more of at will. If I tell my program to make 3 points, my computer will create 3 points identical to the point prefab and place them wherever I want to. With this knowledge, I created a script that would be in charge of rendering my points, and eventually, a triangle.
In my script, I made 2 functions. The first function is called render triangles. Right now, it instantiates the first point, point A, at coordinates 0, 0. That way, I can build my triangle out from there. The second function simply deletes all points in my program. This is useful because if I render one triangle, and then decide I want to render a different triangle, I need to delete the first triangle before creating the second triangle, in order for them not to overlap. After making those functions, I made a render triangle button, which runs the first 2 functions previously mentioned. Now that my button can render a point, I added 3 variables to my program to represent the side lengths of the triangle. Since I'm naming the 3 points of the triangle, point A, B, and C, my side length variables are AB length, AC length, and BC length. I changed my render triangles function so that it creates another point, point B, at the position of point A plus AB length. I also used a line renderer Unity comes equipped with and drew a line between the 2 points. Now I have one side of the triangle. If I could just figure out where point C goes, then I could draw the rest of the triangle. I tried to figure this out for hours, but I just couldn't manage to figure out where point C would go. It was clear to me that I would need the help of a mathematician to figure this out, and luckily, I knew just where to find one. Kevin looked at my problem, and after a while of thinking and hopefully doing his job, he gave me 2 formulas to help me figure out where point C would go. The first formula is the previously mentioned law of sines. The law of sines formula can tell you all the side lengths and angles of a triangle with any 3 pieces of information, except for 3 angles, since you need at least one side length to know the scale of the triangle. This formula is super helpful, and I knew before I had talked to Kevin that I would need to implement the law of sines at some point, but I wasn't sure how I could use the law of sines to get the x and y coordinates of the third vertice. That's where Kevin's second formula comes in. I couldn't find the name of the formula online. Maybe it's also a part of the law of sines, I'm not sure. So I decided to call it the third vertice law, because I thought it sounded good at the time. The formula has two parts. One part finds the x-coordinate of the third vertice, and the other finds the y-coordinate. The x-coordinate is found with the equation x equals AC length times the cosine of A angle. And the y equation is very similar and is written as y equals AC length times the sine of A angle. I converted both formulas into code. Now my program uses the law of sines to figure out all angles of the triangle. Then, the third vertice law uses a side length and an angle to figure out where point C goes. Kevin also told me that it would be easier if I had the longest side of the triangle on the bottom, so I edited my code to plot the points that are part of the longest side on the bottom. After I did this, it finally seemed to work. If I gave my program 3 side lengths of a triangle, it would construct the triangle flawlessly. I was happy with the progress I made today, but there are still things I needed to work on. Currently, the program only works when 3 sides are inputted, when there are 3 other combinations of sides and angles that can also make a triangle. I put the code that calculates the triangle information with 3 sides into a separate function, called SSS, or side side side. Now when you press the render triangle button, the render triangle function is called, which checks if 3 sides are inputted. If so, then the SSS function is ran. If not, then nothing happens yet since I don't have the other functions. Now, what I need to do is put the other side and angle possibilities into different functions, make sure the user can't input numbers for an impossible triangle, and label the triangle with names, angles, and side lengths. But all that stuff is for another day. Hey, remember when I said the program can construct triangles flawlessly when given 3 side lengths? Well, it turns out it can't. I double-checked the angles and side lengths of the triangle, and it sometimes makes the correct triangles, but not always. It took me the entire day to figure out the problem. At one point, I even asked Glenda if she could help me with figuring out the angles for the top vertice of the triangle, because I thought that my code may have calculated that angle wrong and therefore started giving me wrong triangles. In response, Glenda gave me a very familiar formula, the law of sines. Glenda giving me this formula made me realize that I must have done something wrong when translating the mathematical formula into code. I looked at Kevin and Glenda's formulas and my code and had figured it out.
Kevin gave me the third vertice law to determine where point C goes. However, my program changes where each side is located depending on if they are the longest side of the triangle or not. If AB length is the longest side of the triangle, points A and B are placed on the bottom, and point C is on top. Then, the third vertice law formula uses AC length times the cosine of A angle to find C point's x value. Then, AC length times the sine of A angle is used to find C point's y value. This gives the correct coordinates. However, if, for example, AC length is the longest side of the triangle, points A and C are placed on the bottom. AC length is no longer the side that goes from A angle to the third vertice. The program gets the sine and cosine of the wrong side length, and the formula is completely ruined. Calculating the angles has a similar problem, because in order to do so, you need to use the law of sines, which is not happening with this mess of side lengths and angles.
So I made sure my program can recognize the differences in each of the side length situations, and everything seems to be working well again. In other news, I added an isTrianglePossible function, which uses the triangle inequality theorem to determine if a triangle can be made with the side lengths inputted. If you don't know, the triangle inequality theorem simply states that the sum of the triangle's 2 smaller sides must be greater than the triangle's longest side. For example, if you type in 2, 7, and 3 into my program, the function will return false and a message will pop up saying, "It is impossible to construct a triangle with these dimensions, because 2 plus 3 is not greater than 7.
Today is Saturday, so I only spent a couple of hours working on coding. However, I discovered something important during that time. Apparently, my program doesn't actually need to put the longest side of the triangle at the bottom. This is information I really wish I had known earlier, as it would have saved me a lot of time and frustration, but I'm still glad I went through it since I learned a bit about math and logic. Anyways, I edited the code to make the problem less complicated and saved up on space. Now point A will always be the starting point, point C will always be the third vertice, and point B will continue to be point B. I'm not going to be working tomorrow, but I will continue on Monday. Now that all the work is done with calculating the angles of triangles with 3 sides, it is now time to calculate the angles and side lengths of triangles that don't have 3 sides. There are 4 postulates used to calculate triangle side lengths and angles: SSS, SAS, ASA, and AAS. The one we've done so far is the SSS postulate, which, as mentioned, says that we can use the law of sines to calculate the angles of the triangle when we know all 3 side lengths. Secondly, we have the SAS postulate. This postulate states that when we know an angle and the sides adjacent to that angle, we can use the law of sines to figure out the remaining side and angle values. The law of sines can also decipher ASA triangles, which are triangles with a side length adjacent to 2 angles. Finally, AAS triangles are triangles with 2 angles not adjacent to a side length, and also have their own reworded version of the law of sines to discover their informational secrets. I decided that for this day I would try to get my program to be able to decipher SAS triangles. At first I thought I would have to calculate the remaining side and the 2 missing angles. However, I realized that I already have an SSS function that uses the triangle's side lengths to calculate all of the triangle's angles. So all I really needed to do was figure out the length of the remaining side length and then run my SSS function. So I rearranged the law of sines function and got this equation. BC length squared equals AC length squared plus AB length squared minus 2 times AC length times AB length times the cosine of A angle. These values obviously change depending on which side you're solving for. I converted the equation into code and then ran the SSS function afterwards. I tested this by making the angle 90 degrees, and sure enough I always got right triangles rendered. Now that I finished this function, I can plan to complete 1 function a day. This will leave me with 2 remaining days for debugging and adding the labels for the triangle. Today I woke up bright and early at 12 o'clock to try my best at making the ASA function. As mentioned before, the ASA function will take 2 angles and the side between them and use that information to calculate the 2 other missing sides. I would then use the SSS function to gather the other angle information. Since the ASA postulate states that you can figure out the side lengths and angles of a triangle with 2 angles and the side length between them, and you can figure out the third angle of a triangle by subtracting 180 degrees by the 2 other angles, since the triangle's angles always add up to 180 degrees, then, instead of having 2 separate functions for ASA and AAS, I created one function called ASA plus AAS. The function was slightly more complicated than the SAS function, but it was still really simple. First of all, since the function is only called when there are at least 2 angles inputted, the function calculates the third angle by subtracting 180 from the 2 other inputted angles. Once the angles are calculated, the function checks which side length is inputted and uses a reworded version of the law of sines, again, to calculate the other side lengths. Since we still need to place point C, I still decided to run the SSS function again to place point C, even though we already have all the side lengths and angles. I could have just taken the code that calculates point C out of my SSS function, but I didn't want to do that, so... And just like that, we are finished with the functions, and a day early too. Now that we have finished the hardest part of this challenge, I'm going to spend tomorrow getting labels set up on the triangle and moving the camera so that the triangle is always at the center. Today, I loaded up Unity and got ready to implement some camera movement. I created a new script on my camera called Camera Follow. Camera Follow has 2 variables, location to move to and size to move to. Every frame, the camera will use linear interpolation to move a very small distance to wherever location to move to is equal to. Linear interpolation, or LERP in Unity, is just a way to move something a small percent of the way to its end location. In this case, to location to move to, which gives the camera a simple, smooth movement. But what is location to move to equal to? Great question. The render triangle script has one more unmentioned function: draw lines. Up until this point, the draw lines function was pretty simple. At the end of the calculations, if the program decides that the triangle can be rendered, all points are instantiated at the positions previously calculated, and the line renderer draws the lines between each point. What we are left with is a correctly drawn triangle. This is nice, but what does this have to do with camera movement? Well, we want our camera to move towards the center of the triangle. Since at the end of the calculations, we know the length of all the triangle sides, we can use the side lengths to help us figure out where the center of the triangle is. Because point A will always be at coordinates 0, 0, we can take the length of AB, divide it by 2, and that gives us our x value for the center of the triangle. Now, because point A is at position 0, 0, and point B is at position AB length 0, we know that line AB has a y value of 0. So, location to move to's x value equals AB length divided by 2, and location to move to's y value equals point C dot transform dot position dot y divided by 2. Now my camera moves 1/100th of the way to its location every frame, which looks pretty good. Next up is size to move to, which was a lot more simple to make. First, I set size to move to the longest side of the triangle, and that's it, we're done. Finally, we need to label the triangle. It took me a while to get familiar with Unity's Text Mesh Pro system, but I figured it out. First of all, we have 3 side length text boxes, 3 angle text boxes, and 3 point text boxes. These texts are hidden at the start of the program and at the beginning of generating a new triangle. This is because, in the event that the triangle is impossible, we do not want to have useless labels shown. If the triangle is possible, then the text boxes are unhidden, and we begin the process of labeling and positioning the text boxes. The point text boxes represent the points and are labeled A, B, and C. The side length text boxes are equal to the side lengths rounded to the hundredths place. This way, we don't get a number with 7 decimal places. The angles are labeled the exact same way except with angles instead of side lengths. Duh. Now that everything is labeled, let's place some stuff. The point labels are placed at the points they represent and are moved slightly away from their points so that they don't overlap. The angles are similar in that they are also placed on their representing points, except they are moved slightly inside the triangle. The side length labels are the most unique because they are placed at the difference between their 2 points, moved slightly away from the triangle's sides. The program also adjusts the lengths of the points and lines depending on how big the triangle is. And after all of that work, it's done. It's finally finished. The program can now take inputs from the player, determine which postulate to use, calculate the missing information, determine where each point goes, draw the lines between the points, and label the triangle. This project was both easier than I thought it would be, and harder than I thought it would be at the same time. In my mind, I pictured each function taking roughly the same amount of time to complete, but it had turned out that after 6 hours of getting the SSS function to work on the first day, the rest of the project was easier, since I could just copy the SSS function and change it around a bit. It was still a lot of work, but I definitely think my strategy of working hard at the beginning really helped make this project easier. Despite all of the challenges, this project was very fun to complete, and now I can use this program to help me with whatever the ability to calculate the lengths and angles of triangles can help me with. All in all, I am very glad that I made this, and also I am very glad that I am done with this. Thank you, and goodbye.